Record. Okay, so here's another video of reinforcement learning doing stuff. This is right over here in the NVIDIA Seattle Robotics Lab, but it's they've trained RL with PPO to do cube rotation. It kind of works. Okay. So that's exciting. So if you want to see it, bother Dieter and he'll give you a tour. But today we are going to continue our journey through policy grading. So last time we talked about policy gradient, what makes it challenging. We talked about variance and the natural policy gradient. And today we're going to get into how to make that practical and try to derive algorithms like TRPO and PPO and so on. Right? Yes. It's interesting. Yeah, I think in terms of algorithm design, PPO is in like 2018. And what people use in 2024 is kind of PPO. And so in policy gradient, I think we've like not made huge advances in the last 4 or 5 years. But in off policy RL, we've made a ton of advances, like in actor critic methods and Q learning methods. I think they work way better, like good enough for us to run in the real world in the last year, maybe 2 years. So I think we're still making advances there. And I think a lot of the advances are trying to understand the dynamics when scaling up. So I think where we are is like the methods are kind of mature and we're trying to like see how they scale up. And so, yeah, I don't think you'll see a lot of very impactful core algorithms work, some, but a lot of it, I think, boils down to how to scale these up, how to apply them practically. Yeah. Yeah, exactly. So you can like, it's like an order of magnitude more efficient, so you can apply it to something like a robotic system in the real world. Whereas you don't want to run PPO on hardware. But yeah, it's a good question. I think there's still space for algorithmic research. It's just like harder to do because the bar is quite high. Okay, so I'm going to do a quick recap, and then we'll talk about what we're going to talk about today. Right. So this is the basic policy gradient. Just to recap, it's saying that the gradient of your return is grad log phi times your sum of rewards. And this is your Monte Carlo approximation, something you can approximate with samples and implement in PyTorch, right? And so all we did is multiply and divide by p, use the grad log, use the reinforced trick, use with the chain rule, and that's just how we derived this, right? And so our basic policy gradient we talked about has several issues that relate to variance, right? We couple together actions. It's susceptible to scale variations and lucky samples, right? So these variance concerns make the sample complexity huge and the optimization kind of unstable. And so we talked about 3 different ways to, or 2 different ways to reduce variance. The first one is with causality, where we just said, hey, we're going to like make our estimates of return not depend on the past, just on the future. So we're going to go from return to go, right? And so that's going to decouple the future from the past and then allow you to reduce variance because at least you're not affected by things in the past. And then after that, we talked about how we can reduce variance with the baseline, and the baseline basically centers your returns. And so doing that makes things less susceptible to scale variations. And so we talked about the baseline and we then derived how it does not increase bias, but it reduces variance. Right? So it's unbiased estimator that reduces variance. And so all we need to do is subtract an S-dependent function B, and that's going to reduce variance. Right? So that's often called your baseline, sometimes called your critic, right? B is sometimes replaced with B, right? And that's often because your baseline is often set to be the expected sum of rewards under your current policy. So the average rewards under your current policy. Right. So that's variance reduction with the baseline. And so we kind of study 2 main techniques for variance reduction: causality and variance reduction with the baseline, right? Then we said there's more issues with policy gradient, the fact that it's not covariant, right? So it's susceptible to parameterization. And if you look at gradient descent, it's basically steepest descent under the Euclidean norm. Right? And we said, hey, maybe the Euclidean norm is not a great norm because the parameters might be scaled differently. And so we kind of went from there to try and work out this natural policy gradient, right? So we said Euclidean norm might not be great. So for deep neural networks, it might be susceptible to parameters of different scales. And so we tried to go from the Euclidean norm to a G norm, and we tried to choose the G norm to be the quadratic approximation to the KL, right? And so one way of thinking about this is you're doing steepest descent. So you're saying taking linear approximation of J, and you're saying find the parameter theta that's best while being within epsilon ball under the G norm, right? Which means that theta minus theta I transpose G, and theta minus theta I is less than or equal to epsilon, right? So it's within this G norm. And we wanted to choose G, so we said instead, we want to choose G in a way that encapsulate the effect on actions on the output of your model, right? And so the way we did it is we said, instead of like just making this depend on the parameters, try to make it depend on how the action distribution changes, right? So we don't want the action distribution to change a lot. And so we said, let's replace that with a KL divergence constraint. And to make the KL divergence constraint like tractable, we just did a second order approximation to the KL divergence constraint. So we did a second order Taylor approximation, right? So you can write this as theta minus theta I transpose times a matrix F, theta minus theta I less than or equal to epsilon. And F is what we call this Fisher information metric or matrix. Right. Does all of this ring a bell? Right. So we've said that is bad, or Euclidean norm is bad. We're going to replace with a different norm. We want to choose that norm. We're going to use the quadratic approximation to the KL divergence so that encapsulates how much the policy is going to change, right? And so you can think of this as like you want to do steepest descent while not changing the action distribution a lot, right? And and so we define this thing called the Fisher information metric. So I'm not going to work through the math. You just need to take the definition of KL divergence and differentiate it once, and you'll get the Fisher information metric. Extra credit if you do. Send me a message. But basically, if you take the KL divergence and do the second order approximation, you'll see that it becomes delta theta transpose times F times delta. That's your like second order approximation, and F is basically the outer product of the gradient. Expectations over like states and actions from your policy. Okay, yeah, we just have this. Yeah, so it's like an expected under your current policy. Okay, so yeah, so you can think of this as like essentially measuring sensitivity, right? So it says how much does pi theta change when you change theta, right? So because this is a covariance matrix, essentially it's a covariance of the gradient. So it's trying to find directions where like changing theta really affects the policy of the probability of the output, right? And so just like a covariance captures directions in which the data moves a lot, like the Fisher information captures directions in which the likelihood is sensitive. Right? And so that's an easy way to think about it. Yeah.
Will there be pi theta I with that?
Yeah, I think it's actually, yeah, I think this is actually theta I. Or like you can just do this whole thing at theta equal to. Good call. Okay, yeah.
This higher level, like, is there a reason why you don't want your policies to change too much in one step? Is that just like a stability case?
One way of thinking about it is if you go back to here, your policies change too much, then you like potentially get into catastrophic. You may take too large of a step, right? And so like imagine you're like you're a humanoid, and then you take too large of a step, then you start collecting data that is right? And so you want to be careful because in RL you're collecting your own data, but too large of a step means your data is going to be bad, so you'll never recover.
If you have something like a run through like a very certain sort of information, like a demonstration, like, is there a way to like?
That's different calculus because that's like a different objective, right? It's not like expectation under your current policy.
Okay.
But yeah, you could potentially use that to inform step size. That's not all.
In practice, I've seen like something like gradient clipping to work.
Yeah. Yeah, that's what PPO is going to do.
Okay.
Yeah, no, a great question. Yeah. So I'm just going to walk you through the journey, and then the ending is going to be wildly unsatisfying. Because the start is going to be amazing, and then the ending is going to be clipping. So spoiling the story for you. Okay. So once you have the feature information metric, you can then derive your natural gradient update as the gradient preconditioned by the F inverse. Thank you for pointing out the theta I, Rohan. I'll fix that. I have to write it down so that I don't forget. Okay, so the point is we went from our standard gradient update, which is under the Euclidean norm, to the gradient update under the KL divergence. The quadratic approximation of the KL divergence is the Fisher information metric. The resulting update is the gradient is preconditioned by the F inverse. The F inverse gives you sensitivity. And so if you're taking the preconditioning by the inverse of F, you're like downweighting stuff that is overrepresented and upweighting stuff that is underrepresented, right? So that you're like actually accounting for things that affect the policy. Right? Yeah. Epsilon affects in the range of in the choice. Okay, so let's try and
In the previous, so we are trying to ensure that the updates to our policy are
not too large.
not too large. Do we actually want to ensure that the changes in our J are not too large, or do we actually want to be enforcing this change to the policy? Like, is the assumption that if you make small changes in policy, there'll be small changes in J, and thereby that's fine?
Yeah, so
Or-
you can show that that's what TRPO does. It shows that small changes in your policy give you like bounded changes in your return. And so basically just saying that it's like you change your policy a little bit, it can only propagate so much in terms of the dynamics, right? So they're kind of connected.
Okay.
Right? But at least the way I like to think about it is you're making changes on your policy. I find it more confusing to think about the connection to return because you have to like account for dynamics. Right. Okay, so I thought this would be a fun thing to derive, but some folks talked about the Hessian last week, right? And said, why is this connected to the Hessian, right? And the Fisher information is not the Hessian, right? So the Fisher information is an outer product of grad log, whereas the Hessian is the like second derivative, right? And so I wanted to work out what the connection is between the Fisher information and the Hessian, just to like provide a bit of understanding, right? But the point of this exercise is we worked out the natural gradient, right? And in optimization, we have lots of like second order methods like the Newton's method, which try to like use the Hessian as F, right? And so what we're going to show is that the Fisher information is kind of an approximation to the Hessian of that thing, right? And so it's going to be your Gaussian approximation to the Hessian. So if you think of this is just your log likelihood, right? If you think I'm going to like do it in the general case of any prediction problem, and you can show that it's true for policy gradients too. So if you have like your maximum likelihood problem, so that is your objective, right? Negative log likelihood over your data set. You really want to study what the Hessian is, and I want to show you that the Fisher information metric is kind of like an approximation to the Hessian. Okay, so you want to take the Hessian is the second derivative of this objective, right? And so as before, you can push the second derivative inside, right? And so what we're going to do, we're going to move the second derivative inside. That's all we did is we moved this thing over here, right? And so, so the Hessian is equal to the negative expected Hessian of log prob, right? Okay, so then what is the Hessian of log prob? Let's first work out, you have log prob. Oh, sorry, y given x and theta. Here's that. Okay, y given x and theta, right? And you want to take the derivative with respect to theta first, and then the second derivative with respect to theta, right? And so the first thing is going to be a gradient, p y given x theta over 1 over p, right? So that's going to be the first derivative. The first derivative like the derivative of log p is going to be 1 over p grad p, right? Same thing we worked out before. And now you can like use the product rule on this, right? So it's, if you want to take the second derivative of this thing, it's a product of two things that depend on theta, right? So you can use the product rule. So the product rule is going to be 1 over p times the second derivative of p plus sorry, the gradient of 1 over p times grad p, right? Like the same thing as, like, all we did is we said that the gradient is going to be the first term, then the gradient of the second term, that's the second term, then the gradient of the first term, just product rule. The product rule is going to tell us it's 1 over p times the gradient of the second term, which is the Hessian, right? Plus the gradient of the first term times the second term, right? And so I will typeset this so you guys don't have to deal with my handwriting after this, but right, so you're just using the product rule here. So now if you like expand this a little further, this is going to be 1 over p times the Hessian plus, or rather minus 1 over p square times grad p times grad p, right? Like the derivative of 1 over p is minus 1 over p squared times grad p, right? Yeah. Yeah, there's a transpose in there. And so, yeah, so the point here is that this gives you a second derivative, and this gives you a minus 1 over p squared grad p times grad p transpose, right? And then, you know, you can write this, the second term, you can write as grad p divided by p times grad p divided by p transpose. Yeah. And so by inverting the chain rule again, right, you can write this as grad log p times grad log p transpose. Right? Same thing we did last time, which is saying that, you know, the derivative of grad log p is 1 over p times grad p. And so you can say each of these terms is equal to grad log p. Right? And so what you get then is directly the Fisher information, right? So the second term is the Fisher information. Yeah. So let's recap the steps. You have your original log likelihood of the gradient. You get 1 over p grad p. You take this, the gradient again, you get product rules 1 over p Hessian plus grad 1 over p grad p. When you expand this out, the second term just becomes sufficient information, right? And so getting rid of the scribble, essentially you can show that the Hessian is equal to like the Fisher information minus some like second order term, right? And so often you're going to like approximate, you can think of this as, this is what you call your Gaussian approximation, where you like throw away like the second order term, and it's like not so terrible. It's like a quasi-Newton method, right? And so the point here is that essentially you can connect the Hessian and the Fisher information. Like the Fisher information is an approximation to the Hessian, right? So it's not actually ever computing the second derivative. It's only taking the outer product of the first derivative, which is better, but still not that good. And the whole, like, viewed geometrically, the reason that like doing things like the natural gradient are good is when you have an objective like this, SGD is gonna like zigzag through the space. It's just taking the gradient. And when you take into account the like information geometry or like the shape of your optimization problem, you get optimization double. And so it gives you things that are like more efficient. And so you can view it many different ways. You can view it as the policy not changing. You can view it as more efficient optimization. They kind of all result from this. You're going to view it as an approximation to the Hessian. They all kind of result from the same thing. Does that make sense? So all that I really wanted to communicate here is that natural gradient is coming from an approximation to the Taylor divergence, but it's also an approximation to the Hessian. It's also an approximation to a second order method. Yes? Okay, good. So this is so old that I couldn't find videos for it, so I only had to screenshot the paper. But this is from Jan Peter's work, and he showed a bunch of cool stuff with natural policy gradient. So he showed you can do like this baseball task, you can do like ping pong, and this was like early 2000s. So I think yeah, it's amazing for that time. So take a look at Jan Peter's work. He's awesome. Cool. So that is natural policy gradient. Any questions before we we move on to why this might not be practical. Good. So before I tell you why it might not be practical, why don't you tell me why it might not be practical? So let's go back to the natural gradient, right? The natural gradient objective is like, what about this is not a practical? Yeah.
From ML. That 1.68.
No one wants to take inverse. Good. No one, avoid inverses at all costs. The other thing you want to remember is that your Fisher information is the outer product of grad log phi. And so imagine you had 7 billion parameters. That means you have a 7 billion cross 7 billion matrix that you're trying to invert that times, right? And so you want to avoid that. What else might make this impractical? Right, so can it's objective, right? How do you fix that? Right, like the choice of alpha clearly determines things, right? It clearly determines how much you move. So let me see. Like for instance, as Matteo was just saying, you choose the alpha wrong, you like fall off the cliff, you never come back, right? And so the choice of alpha is like, it's kind of a pain in the ass. And so we need to find better ways of choosing alpha besides just guessing. Okay, going back to our objective, what else might be a pain? Just thinking about, all the knowledge you've gained about policy variance and stuff. So just to remind you, the way it's going to work is you're going to sample a bunch of data. You're going to compute F, you're going to compute gradient, you're going to compute F inverse gradient, and then you're going to take a step and you're going to collect a bunch of data again. Repeat.
Because you're taking samples from when it's the S.
Right. The F might be like not estimated, but that's yeah. So you might still have like a high variance problem. The variance could still be an issue. The other problem is that this objective is like on policy, right? And which means that every time you have to evaluate this objective itself, like J theta, depends on like samples from the environment, right? So anytime you need to take gradient steps on the objective, you need to take samples in the environment. So essentially, if you look at the definition of, let me see if I can go to start. Like if you look at the definition of J theta, right? Maybe I don't have it here, but if the definition of J theta is just, the expected return of your trajectory sample from pi theta, right? The problem is this, if I want to do like in normal gradient descent, right? What you do is you like start at some theta I, you evaluate the gradient, you take a step, then you evaluate the gradient again, right? And now the problem here is that the objective depends on samples from theta. So every time I want to take a gradient step on the objective, I have to take samples from theta, right? Which is like horribly expensive. But like I want to do like in optimization, you run many gradient steps typically. Every time I have to do a gradient step, I have to take samples from theta, which is like a huge pain in the ass, right? Because like every time you have to, like even if you want to take little tiny steps, you have to keep resampling every time. So that's kind of a pain. And so that kind of leads us to, the requirement for better methods is because of these three problems, right? So the problems are these three, right? You have on policy updates, like I was just saying, like every time you need to take a step on the objective, you need to like take samples in the environment. Okay. You have this huge matrix inversion problem, right? You want to avoid inverses at all costs. And it's hard to choose step size. And sometimes your step size might be too large, it becomes hard to tune. And so you want better methods to choose step size, right? And so if you want to make natural gradients, and natural gradients has advantages in that it like obviously avoids the zigzagging issue, it avoids sensitivity, it's generally more performant. But if you want to make it practical for like neural nets, you need to deal with these problems. Right? Does that make sense? Okay, so we're going to deal with these problems and then we're going to make this kind of stuff happen, make a humanoid walk. And this is a video from John Shulman in 2015, but essentially he proposed a method called trans-region policy optimization, which kind of, I'd say, like kickstarted a lot of continuous control in RL with deep neural networks. And the key things he did is he looked at natural policy gradients And then he kind of like made these three changes to make it practical to train with a big. Right. And then he realized that all of this was for naught, and then he did clipping. But before that, but these things will connect, right? But does that make sense?
I have a question about the remote.
Yes.
Special information matrix,
Yes.
like it's a classic matrix.
Yeah.
What does it mean? What's the fact?
Oh, you're saying it's not invertible?
Yeah.
Yeah, because you're taking expectation over by theta. It should still be invertible, no? Like, how about we let me circle back to you on this. I think I need to give it a little more. Good. You're saying that because it's like grad log pi times grad log pi transpose, it's a rank 1 matrix, which means it may not be invertible. Yeah. Yeah. Right. That's what he was saying, but that's what you're saying about expectation, right? So it's like linear combinations of rank 1 matrices.
Still might.
So it might not be invertible. Yeah. Right. Then you can do something like the pseudo inverse. Yeah. But I think his point is that it's like, is it even well defined, right? Because if you have a rank 1 matrix, not invertible. But if you have the expectation of a rank 1 matrix, that might be invertible. But yeah, let me get back to you with some more details. I don't want to say something that's not accurate. Okay, so these are 3 ideas that we're going to talk about in TRPO. Right? So let's kind of go through them one by one. So the first idea is that we want to go from having these on-policy updates to things that are important samples, right? So things that allow you to be off policy. And so the problem with the original policy gradient objective is that it's hard to evaluate without samples from theta, right? So if you have your objective theta, which is the expected reward, you sample trajectories from p theta tau, right? Every time you need to evaluate this, you need to take samples from p theta tau. You cannot evaluate it otherwise. Right? And that makes the gradient hard to evaluate without samples from p theta tau. So if you need to take multiple steps, it's like hard to do without getting samples. And you really want to just like kind of take a bunch of samples, do some gradient steps, take a bunch of samples, do some gradient steps. And so you need to sample to evaluate, which is a pain. And so the question is, can you be off policy? Can you like not have to resample all the time and still do these grades? And so the trick here is to use this technique called importance sampling. How many folks know about importance sampling? Okay. So let's try and derive it, right? So if you have your expected return as the expected your expected return as the expectation under p theta tau of r tau, you can do our favorite trick of multiplying and dividing by some distribution q. Right? As long as q and p have overlapping support, you can multiply and divide by your distribution q. And you can rewrite this. You can basically group these two terms together, right? And rewrite this as now an expectation under q. Right? And so you can rewrite this as the expectation under q of r tau, which is reweighted by p theta tau by q. Right? So this is not specific to RL or policy gradient or anything, but it's saying that you can evaluate some expectation under p using an expectation under q, but reweighted by the density ratio between p theta and q. It's an arbitrarily chosen distribution, right? So it's just a distribution that has overlapping support, which means that everywhere where P has likelihood, Q has likelihood. And so all you need to do is pick some Q. The different choices of Q can be differently good. You pick a Q, and then you can evaluate J theta by sampling from Q. Right. So the nice part, but you need to know this density ratio. You need to be able to evaluate P theta tau by Q tau. right? And so you can think of it as like, you take samples from something that's easy to sample. Let's say you had like a data set which had some distribution Q tau. As long as you're able to compute P theta tau by Q tau, you don't actually need to take samples from P theta tau. You can just reweight the samples from Q tau. Right? That's the basic idea of importance sampling. Right? The only condition is that you need overlapping. So the point is, we want to be off policy, right? So you can just take J theta and write it as an off policy objective in terms of Q tau, right? You say sample trajectories from Q tau, you just reweight them by P theta tau by Q tau. Okay, and so why do we want to do this? Like, why would this?
Because now you can sample trajectories from this other.
And you just keep it stationary, right?
Required.
Yes. Right. The second point is that, so the advantage is that you could be off policy, but the challenges are that you might have some numerical challenges, which we'll talk about in a second. And interestingly, you can rederive policy gradient from this importance sampling perspective, which will make art like that. And so let's start by rederiving policy gradient from the importance sampling perspective. We'll talk about the numerical challenges and some approximations that can make it okay. So why, like, just to connect it back to everything we're talking about, why do we care? We care about it because we want to go from these on policy updates to updates we don't have to keep sampling things from, right? And so what we're going to do is we're going to use importance sampling. And let's start by rederiving policy gradient from the perspective of importance sampling. Yeah. And so this was our derivation of importance sampling. Let's try and show how under a particular choice in Q, you can rederive the policy gradient. And so what we're going to do is we're going to take the gradient of this objective, right? So you're going to take the gradient of this important sampled objective, right? And so now you'll notice that if you take the gradient with respect to theta, the expectation doesn't depend on theta, right? Which means that you can just like push the expectation inside, right? So now the expectation, the gradient of your objective is going to be the expectation of grad p theta by Q tau, grad p theta by Q tau times R tau. Now, what we're going to do is we're going to set Q tau to P theta I tau. So it's like the trajectory distribution, your current trajectory distribution, your current policy. And so you're going to set it to P theta I tau. So you can rewrite your gradient now as trajectory sample from P theta I tau of grad theta P theta tau divided by P theta I tau. So all we did is we replaced Q tau by P theta I tau, right? That's all we did. So we just important sampling, you took the gradient, which the gradient inside, replaced Q by P theta I, where theta I is your policy parameters at the ith iteration, right? And then all we're going to do is we're going to try and evaluate this objective at theta equal to theta I. Right? So when theta is equal to theta I, this becomes theta I. So this whole thing internally, you can write it as grad log p theta, right? And so you can show that the objective, when you take the gradient, gives you exactly the policy gradient, right? And so you can show there's like, you can rederive the policy gradient by taking the important sample objective and set the sampling distribution to be your current policy distribution. And so the nice part is then you can, at least in the first order, this objective matches exactly the policy gradient objective, right? And so often you'll call this objective with Q equal to P theta I as your surrogate objective reinforcement. And so the point is that it's a surrogate objective whose gradient matches the policy gradient. Yes? So the point here, all we did is we said this J theta is exactly equal to this thing. And if you take the gradient of this thing with Q equal to P theta I, you directly rederive the policy gradient. And the on policy the standard policy. So that's like just a nice connection to rederive. Make sense? Okay, yeah. It only matches at that point in first order.
What do you mean by first order?
Like you have an objective and you're taking the gradient of the objective, and the gradient of the objective matches, but the objective may not be the same. Right? Okay, so the important thing here is just to to see that important sampling makes sense, and it can like allow you to rederive the policy gradient, right? When you set Q equal to P theta I. So now let's go back to our original problem. We wanted to go from something that's on policy to going to something that's off policy, right? Like we don't want to have to keep resampling things. And so now important sampling gives us a way to do that. We sample from some Q tau, which is great, right? And we don't need to keep resampling. You can keep taking gradient steps on this objective, and you like there will be gradient steps on this, but you just have to like keep reweighting like. Okay. Now, why might this be a problem? Like just this objective has currently written, what might be like challenging stuff? Take this J theta, you can do gradient steps on this, everything works out fine. Like why is this objective kind of not a big deal? So you can keep Q tau fixed. You can keep Q tau fixed, right? Because you can just like you can have the same Q tau and have different P theta taus as long as you change the read weighting term. So the issue here is that it's actually that you're doing these are called importance weights, right? And the importance weights are computed over the entire trajectory, which means that like they can be written as the product. Like if you write out the definition of P theta tau and Q tau, right? So P theta tau is basically P of S naught times P of S1 given S naught A naught times pi theta of A naught given S naught. Repeat. Right, same thing we did in policy gradient lecture 1. And Q tau is going to be P of S naught times P of S1 given S naught A naught times Q of A naught given S naught. Repeat, right? All the terms will cancel out except for the policy terms, which are different, right? The dynamics of the environment are the same. In both trajectories, the only things that are different are the policy terms. But you cannot like, you can't, they're not independent. So you have to like multiply all the probability terms across all the time steps in the numerator and in the denominator. And so what you have is this importance weight, which is like a product of a bunch of density ratios. So you take like likelihood at every step, multiply it along the whole trajectory, and likelihood at every step in the denominator, multiply it along the whole trajectory, then you take the ratio of those. Right? And so the problem with that is that it's like super numerically unstable. You take a bunch of multiplying things in probability space is always unstable, right? And it's like they tend to either blow up or collapse. And so typically doing important sampling, where you have to like multiply a bunch of probabilities is a huge pain. Like doing it for one time step is okay. Doing it for like a huge number of time steps is okay. Okay? And so the tricky part here is that your importance weight is over your entire trajectory, and so you have to like multiply the weights at every time. Right? So that's kind of a pain to guess, right? And so we want to like avoid that. Does that make sense? So from the top, off policy, on policy bad, we went to off policy with important sampling. Important sampling is good, but important sampling has this like importance weights blowing up. That's huh? It's still, I mean, it's still unstable. You still have to multiply a bunch of stuff, right? Or I guess you would add stuff, but that then like you'd still have like a bunch of terms that are coupled together. And so then you encounter issues with variance. Unless you have like a huge number of samples, you encounter issues with variance. Yeah.
Well, I think what you said about how we moved it on policy, because if you said Q of tau the P of theta I tau.
Okay, yeah.
Back to theta, C theta.
That's a good question. Yeah. So you can set it to P theta I tau, but you don't have to set it to P theta I tau. So imagine we took this previous objective, right? This, and you computed you computed the gradient of this thing, setting Q tau to P theta I tau, right? What P theta I tau, right? You did that. And then you moved theta from theta I to theta I plus 1, right? You can continue to use P theta I as your sampling distribution to take multiple steps after that, right? So you can choose whatever distribution you want for Q.
So does this look like you freezing the weights of your agent and then sampling from the environment without having to update it?
The other way around. You freeze the samples and you update the weights of your agent. So it's like, sorry, let me just get rid of the scribble. This is your samples from the environment. You're freezing those, and then you can take multiple updates of theta. Right? So like essentially Q is not changing. Q is going to be for multiple gradient steps, you're gonna freeze Q. And then you can take multiple steps on theta. Right? And so you can start, let's say you set Q tau to P theta initial. Right? And then you like sample a bunch of stuff. And then you can take a bunch of steps on P theta, evaluate it under P theta initial.
Okay, so you can like set like 5, 6.
Yeah, exactly.
But you're just taking that first.
Exactly. And then you go from theta initial to theta 5. And then you can replace theta initial by theta 5 when you take more samples in the environment.
So it's just they're not policy, like the way.
Yes.
The needs, like you said.
And you can use all your previous data because now as long as you reweight previous data, right? So it's like the Q and the P theta don't have to be the same. Right. So the point is that I can keep moving P theta while keeping the same Q.
I guess it's so confusing because it seems like you can only rederive the pulse gradient if you set it equal to something like P theta of I, and then sort of set it to something else.
Right. So we can rewrite the policy again that way.
Yeah.
And that just to show the connection. But the point is that this objective and this objective are the same. And I can keep taking gradients on this objective. Like I can keep taking gradients on this objective with respect to theta, and I can keep evaluating it off policy. This is what you call your, as long as you keep reweighting this. Right. So this is the on policy gradient. So I'm showing you that if you set theta equal to theta I, you can rederive the on policy gradient. And if you set Q equal to something else, then you derive the off policy gradient. Okay, so the point here is that we did importance sampling. It lets us be off policy, right? Importance sampling lets us be off policy because you can keep Q fixed, take multiple steps on theta. Okay. Now, the challenge is that it becomes numerically unstable. And so what we're going to try and do is try and reduce this thing, which is a product of a bunch of density ratios, to like one thing, like not a product. Right? We're going to try and reduce it to like one ratio, not the product of a bunch of density ratios. Okay. So our original objective is trajectory sample from P theta tau, r tau. To rewrite this in stationary form, right? If you remember our first lecture, you can rewrite it in stationary form. So you sample S from the marginal distribution P theta S. You sample A from pi theta A given S. Right? That's just your marginal form of your trajectory distribution. It's the marginal form of your objective, right? And if you have this as your objective, then you can still do, importance sampling here. So this is just the same objective. All I did is this is the same objective. I just re-express it in stationary form. Okay? And so now I can take this objective and again do importance sampling on same thing, right? So importance sampling, if you remember, is if you have some expectation with respect to P of F, you can write as expectation with respect to Q of P over Q times F, right? It's always true. And so what you can do here is you can say this distribution here is going to be my Q, right? So this is setting your Q as P theta I S times pi theta I A given S, right? And then I can rederive the whole update with importance sampling. Same thing, right? Just a standard importance sampling update. We're going to, sample from this Q distribution and just reweight P theta, pi theta by P theta, I pi theta. This is just a re-expression of what I wrote in the last slide, right? And so all of the like multiplication I talked about in the last slide basically reflects in like this term. So P theta IS is the marginal distribution of states, which has to take into account like how states evolve over time. And so this ratio of P theta by P theta I is kind of a pain in the ass to compute because it has to take into account how states propagate over time. And so what we're going to do is we're going to ignore it. So we're going to set this to 1. Right? And so what we're going to say is that we're going to do importance sampling. So we're going to set the ratio of the state distributions to 1. And so you're just going to be concerned with the ratio of the action distributions. Bottom is pi theta I, sorry. Right, so all we've done is we've said, this is just plain old importance sampling. So this is equal to this, like this and this are the same. No changes. And all we're going to do is we're going to take this P theta by P theta I and then just like treat it as 1.
And what exactly, why is it incomplete?
Because it's the marginal distribution, right? So which means, so the marginal distribution means that you like have to run it out over many time steps. And so you have to compute that over many. So that's the tricky part. And you don't know the marginal distribution. You know the policy distribution, but you don't know the marginal distribution, right? And so it's a pain for both reasons. But what we're going to do is we're just going to set this to 1, which means that you're basically going to ignore the mismatch in states. Right? Like pi theta and pi theta I will go to different states, but we ignore the mismatch in states. And what that allows you to do is it allows you to rewrite your objective as under like pi theta I. It's like taking samples from pi theta I, but not having this like product of terms inside the importance sampling, or not having a marginal distribution inside the importance sampling. Right. So the issue with importance sampling was that we had this like product of terms, essentially, which is the same as like having a ratio of marginal distributions, because marginal distributions are over many time steps. And what we want to do is we want to kind of reduce it to a single time step. And so we're just going to ignore the mismatch in state distribution. So like, yeah.
There's not actually.
Yeah, that's okay. Another fixed theta I. So what happens when you typeset things at like 2 a.m. Okay, so the point here is that we ignored this mismatch. Like, that's kind of crazy, right? Why? Like I just said that the state distributions are different, but I don't care. Like, why is that okay?
So because we showed earlier, you try and use get your information to like stop changing your parameters by too much, like it won't actually change by any time by too much.
Perfect. Right. So it's okay when pi theta and pi theta I are pretty close. Right. So it's like if pi theta and pi theta I have like bounded divergence, right? You can show that if pi theta and pi theta I are relatively close, then p theta and p theta I, the state distributions are relatively close. And you're going to like optimize some lower bound on things, but it's not going to be a horrible lower bound. Right? And that's what the TRPO paper shows. Like a little too involved to get into in class, but the intuition is just that you ignore this mismatch distribution, and it just amounts to saying that as long as theta and theta I are close, like ignoring it is not going to be so bad. Yes. Okay. So let's kind of like, put these pieces together. This is often what you call your surrogate objective for TRPO. It's like your important sample objective, ignoring the state distribution mismatch. So you're saying, why does this matter? You sample some samples from your theta I distribution. You sample your policy, and then you put multiple steps on this objective, and you don't have importance weights going. And so the nice part about this objective is that it's off policy, right? As in you can evaluate it under theta I, and you like, as long as you don't take too many steps, like that approximation is okay. Yes. Yes.
Why do you need
Yeah. Okay. So a good question. So if you have Q, which is basically the sum of rewards, right? You remember we subtracted a baseline, right? So if you call this thing Q, and you call this thing V, right? The baseline is V, and the sum of rewards is Q. So normally what you do here in this Q is that you just do the Monte Carlo sum of rewards. So you just compute the sum of the return to go in the future, right? And that's going to be your sum of rewards in the future, and you're just going to subtract the the average return there, and that's going to give you an advantage. Right? It's an approximator for that. Okay, so we covered a bunch of stuff, but before we go to the next thing, let's recap, right? We had a problem with continuously sampling, so we said we're going to importance sample. That's going to let us be off policy. Importance sampling has numerical issues, so we're going to like ignore the state distribution mismatch, so it just becomes one time step, and as long as the policies are not too different, it's an okay approximation. That's all we did.
So like you said, importance weight are very difficult.
Yes.
But then like I think for the distribution states, like if data are not so different, why ignore the
So because you're like doing it over many, many time steps, right? So you're multiplying a bunch of likelihoods, right? No, you're doing like here, like in the previous objective, we are multiplying many, 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 many time steps. And that's what's going to make it unstable. Whereas here, you're just doing one time step, right? And that's what makes it reasonable, right? Makes sense? Yeah.
And then, just use those samples, keep a track of those probabilities.
Yes.
And then do multiple variants.
Exactly.
And then maybe come back and do this.
And then do sampling. Exactly. Right. So, but as opposed to on policy, which literally lets you do one variance step, you can do multiple variants. Steps. You have to redo it. I guess it depends on the domain, but like not like it's like 5.
So this will like speed it up by
Yeah.
5 to 10.
Yes. Yeah.
So here you're doing it in the stationary distribution case, like.
But like essentially what you're doing is you're like sampling from the stationary distribution and just sampling from the distribution. Like you just sample points, like you just sample rejects.
Okay.
Like essentially sample like as long as you're like sampling from your environment, like this thingy is the same as just sampling trajectories. Like sample trajectories, jumble them up. Okay. That makes sense?
Yeah.
Okay. So that was the first insight. Before we get into the second insight, we should take a couple of minutes, digest, and we'll come back in 3 minutes. Yes.
Question,
Yeah.
over time, do you throw away like past trajectories that are like pretty low likelihood?
Yeah.
Out or like policy has.
Yeah, exactly. So what you're gonna, because you can't ignore this mismatch if theta I and theta are very different. So you can only use theta i's that are pretty close to the current theta.
I see, so you
So
throw away.
you
the, like,
throw,
things that are,
yeah.
like back.
Exactly. Which is why you still need like these Q learning type methods, because they let you like retain all the data. And so policy, again, this is a little bit better than what we had before, but because the policies have to be close, you can still only take a few steps. Yeah.
Not fully understanding, but this is like pi theta I is like your policy at iteration I, like the weights of the at iteration I.
Right. So like let's say you have two different things. You have like sampling iteration I.
Mhm.
Like let's say at time step I, you sampled you sampled a data set DI. Okay.
Okay.
And then you at this time step you have some theta current.
Mhm.
What you're going to sample a bunch of stuff from okay, let's call you sample a bunch of stuff from theta current,
Okay.
and then you're going to like take a bunch of gradient steps on theta current to beat theta current prime. Right.
Okay.
And then you're going to set theta current prime as your new sampling distribution, and then sample some new data, DI plus 1. And then you're going to take a bunch of steps to get to like theta current prime, right? So in policy gradient, the sampling iterations and the policy iterations are completely matched up. Like every time you take an update on the parameters, you also have to resample.
Mhm.
In here, they're like mismatched, as in you can sample once, take a bunch of gradient steps, and then sample again, and then take a bunch of gradient steps and sample again.
Okay.
Right? Does that make sense?
Yeah. And the Q thing, I guess, how do you know your Q is like reflective of?
It's just your sum of rewards. It's
Okay.
like the same thing as we had before.
Oh,
It's just like your sum of rewards.
okay. And you're waiting by your sum.
Exactly.
Okay. Thank you. Yeah.
Yes.
As well as the scaling part of the navigating, like one of the stuff you can have to find. So
Which thing, sorry?
the scaling part,
Which one, sorry?
scaling.
Which one? Which scaling? I mentioned scaling like 5 different times. Like, do you mean the baseline?
No, I mean, just.
Oh, scaling as in like
Yeah.
making it bigger. Yeah. I think people have tried it a lot for PPO, and it tends to work pretty well because PPO reduces to first order optimization to SGT.
But they have to fitting a bunch of images.
No, you have to still sample. Right, so you still have to do RL, but it's more stable because you're not doing second order optimization. People have found off policy RL is a lot harder to like stabilize because it's not actually gradient descent. It's like a different objective. And so on policy RL, people have scaled successfully. Off policy RL is still a question mark.
You know, scalar, how
I don't remember the number of parameters, but like across like multiple Atari games and tens of millions of parameters.
So, like, scaling RL, does that basically mean like, we any longer?
Or train bigger models. Yeah. Yeah, I guess I got confused because scaling is also referring to like
Yeah.
multiple scales and yeah. It's a good question, yeah.
And then just to clarify, so for TRPO, like, are we doing parameter updates still after like every single step?
Yeah, you're so updating theta, but you're not updating theta I,
Okay,
right? So you keep a batch of samples. Yeah. And then you like update theta, but you keep reweighting by theta.
Okay, so you're still like running inflation over like.
Yeah.
Oh, I see, okay.
Right. So but it's just like you have a fixed batch of data and that allows you to improve the parameters.
So you're saving like the data flow.
Exactly,
Okay.
which is like the expensive part. All right, so we had a bunch of good questions at the break. Yeah,
You also. The. Yeah, you like.
yeah, otherwise well, if you're keeping your data fixed, right, then at least the denominator remains fixed, right? Sorry, this is data. Yeah, but like the denominator remains fixed, right? Because you're like the S and the A are the same. So as long as everything in your replay buffer is evaluated, like you can do it once. But if you like, for instance, if you like if you didn't have those cached in memory or your, replay buffer is changing, then you have to keep the parameters. But usually you can just cache them. Okay, so a few things that came up in the break that I think were really good questions, which are really good clarifications. Q is just the expected sum, or Q is just the sum of rewards in the future, so return to go. So the way you implement this is Q is just like the same thing we did policy gradient, it's sum of R from the current time steps to the end of the shift, which is the sum of rewards. The second thing that Raymond just brought up is like, how does the procedure go in terms of sampling? So what you're going to do is you're going to have some theta I. You're going to collect a bunch of data, di from it. And then you're going to like improve theta I with a bunch of gradient steps, right? And then this, after many, many gradient steps, you'll call that thing like theta I plus 1. Or not many, some number of gradient steps. You'll call it theta I plus 1. And then you'll recollect data di plus 1. And then you'll repeat, right? And the difference from policy gradient is that in policy gradient, you're going to take like one gradient step, right? You're going to say theta I gives you d, or theta I gives you di. And you take one gradient step, this gives you theta I plus 1. You sample again, gives you di plus 1, you repeat, right? And so the benefit you get is that you can take many gradient steps without having to recollect all the data, right? Yeah. I think it's just a hyperparameter per domain. Yeah, I don't know if there's any prescriptive rule there. Okay, and so that is the first idea. How are we on time? Yikes. That's the first idea, which is important sampling, right? And so the nice part about important sampling is lets you take multiple steps. But the approximation is that you ignore the mismatch in state distribution. And so you can't take like an infinite number of gradient steps, and you have to constrain the policies to be close to each other. Now, the second problem in natural gradient is that, as we've talked about, it's challenging to compute F inverse and get F inverse G. And like if I have to explicitly compute an inverse and then do a matrix vector product there, that's kind of a pain, especially with a large model. And so what we're going to try and do is convert this into an iterative minimization problem whose solution is equal to F inverse G. Okay? And then we're going to try and use an efficient method for doing this iterative minimization, right? And so the point here is that computing F inverse like explicitly is a pain, but we don't care about F inverse. We only care about F inverse G, right? And so what we're gonna try and do is we're gonna construct a problem whose solution is equal to F inverse G, and then we're gonna use an efficient method to solve it. And that's gonna make our and we're gonna do it in a way that doesn't require inversion. Right, and doing so will let us like avoid this F inverse G computation, which is painful in memory and compute, and bad idea in general. Yes? Okay, so the key insight is that your solution to Fx equal to G is the same thing as the solution to your quadratic, right? Quadratic minimization problem. So the solution here is equal to F inverse G, right? The solution here, take the gradient of this thing, is going to be Fx minus G is equal to 0, which means that X is equal to F inverse G, right? So the solution to this minimization problem is also F inverse G. So if you find an X that minimizes this quadratic, it's also equal to F inverse G, but you don't have to explicitly compute the inverse anymore. Right? All you need to do is solve this optimization. Right? So all you've done is you've converted your matrix inversion problem into a quadratic optimization. Yes? So you just convince yourself by taking the gradient of this thing and setting it to 0. So that's good. You've avoided inverses, kind of, but like, why is it like, how do you solve this problem? Like, what's the solution to solve this problem? With Newton's method, you have to like invert the, the thing again, right? So let me say it's the concrete gradient. Right. Okay, good. Well, you can do it with gradient descent. You can do it with gradient descent, right? But gradient descent is going to do things like, it might take a lot of steps, which might make the whole procedure pretty expensive, right? And gradient descent, its trajectory through space is going to look something like that. And you like kind of don't want to solve the F inverse G problem, you don't want to have to like, you know, have a really expensive procedure. And so what you're going to use is this technique called conjugate gradient, which is like far too rich of a problem for me to describe in any meaningful detail, but I'll just give you the intuition and you should read it. And I've linked a really nice article at the bottom. Also in my, can't see it, but it's in my slides that I posted. Yeah, it's very good. But the idea behind conjugate gradient is just, it's kind of like the idea behind coordinate descent, right? It's just saying that gradient descent is like just taking steps in the direction of the gradient, right? But if you can like decompose the objective into like the orthogonal directions, you can just do like these steps to get to the solution, right? And so what conjugate gradient tries to do is it tries to find the what you'd call F orthogonal directions and tries to take steps with this like these D F orthogonal directions. And so what I mean by F orthogonal is that orthogonal will be D transpose D is equal to 0, right? Or DI transpose DJ is equal to 0, like two different directions have 0 dot product, which means they're orthogonal, right? But that doesn't account for like the geometry of your problem. And so what conjugate gradient tries to do is find directions that are F orthogonal, which means that DI transpose FDJ is equal to 0. So that is DJ. And in doing so, it's essentially going to like find like it's going to be able to take much bigger directions through the gradient space because it's not like repeating computation. So it's trying to make every step kind of orthogonal to the last step. And so it's going to converge in a lot fewer number of iterations than gradient descent, right? Especially if your matrix F is sparse. And so we're going to keep moving for the sake of speed, for the sake of time. But like the point here is that conjugate gradient is just an efficient method to solve that quadratic optimization problem. You can solve it with other methods.
Do not use constant gradient.
It's generally not as like, especially with this, like stochastic mini batches and so on, it's like not as stable as just stochastic gradients. It's a good question. Yeah. Empirically. Okay, so the second idea that we talked about is that you have this huge matrix inversion. we converted this matrix inversion problem into a quadratic minimization problem, and we used conjugate gradient to solve it. You could use other methods, but they use conjugate gradient to solve it. And then the last problem is the one of choosing step size, right? And so the issue with choosing step size, if your step size is too big, you kind of overshoot your optimum, right? And it's like not always clear how to choose your step size. And so they're going to use a simple idea called backtracking line search, right? Which is saying that you choose a step size, you evaluate your objective, and then you like decrease the step size till your objective is sufficiently ascending, right? So you can say that, for instance, you chose this as your step size, right? It was too big because like this, let's say you like had a threshold of like, you need to increase by this much. Like this objective was too big because it like overshot. So what you're going to do is you're going to try and drop the step size by some factor and try again. You're going to try and drop the step size by a factor and try again, right? And so you're going to use this, this backtracking line search objective. So it's going to say that you're going to start with some parameter B, which is your like shrinkage parameter. So it's saying like every step. So the idea of backtracking line search is it just helps you choose this like alpha term, right? In your gradient descent objective, you have this alpha term. And what backtracking line search is going to do is going to help you choose alpha. And the way it's going to do it is it's going to start by computing a maximal step size. Let's call it like T max. And then it's going to keep like multiplying T max by some beta, which is less than 1, till it like satisfies some stopping criteria, right? So it's saying that initially you chose beta to be too big, right? Which means that I like, let's make this example more extreme. So like, let's say this thing was like over here. You made it so big that you like just went down, right? And so what you're going to do then is you're going to say, okay, that was too big. Let me like reduce my step size to something better, right? Something smaller. So I'm going to multiply it by beta. It's going to give me something here. Still doesn't satisfy my stopping criterion. So I'm going to multiply it by beta again. I'm going to get something here. Satisfies my stopping criterion, and then I'm done, right? Yeah. You already know.
So.
But it's pretty quick. You just like run it 5 times. And it would have been a pain if I need to evaluate this thing with samples every time. But because I've done important sampling, I don't need to do this. Right? And so that's what makes this like doable. But yeah, good question. Okay, so the basic idea behind backtracking line search is you just have like you start with a maximal step size, and so the way you choose your maximal step size is that you just like take your trust region constraint, right? Your fish information metric constraint, and then you try to like set that to the maximum. You set the epsilon, and that lets you pick the like biggest step size, right? And then when you pick that biggest step size, all you do is you like keep shrinking it by beta till it satisfies some stopping criteria. And often these are like tuned by hand, like your choice of beta is a hyperparameter, and your choice of stopping criterion is a hyperparameter, but it tends to work better than just like fixing an alpha. Right? And so all you've done is like your search direction S is going to be equal to F inverse G, which is coming from conjugate gradient. Right? And then all you're going to do is you're going to say, sorry. Yeah, all you're going to do is you're going to say, I chose S equal to F inverse G, and then I kept shrinking it by beta. I kept shrinking my step size by beta till it satisfies my stopping criterion, and I'm not going to overextend. That's it. Okay, so let's put all the pieces together. There's 3 ideas here. The first is to try and convert your on-policy updates into your important sample objective. Won't we spend all this time on it? Basically, it's just trying to replace the important sampling objective and dealing with this like this blowing up term by just ignoring it. The second thing is saying you want to avoid matrix inversion, convert into minimization, solve with conjugate gradient. And the third thing is saying your step size might be too large, you just do backtracking lines. Right. Those are 3 ideas in TRPO. I find the paper extremely hard to read still, but maybe these will help you all read it. Okay, questions? Does this like so how does this relate to natural gradient? Right? Natural gradient was just I don't know if I have it here, but natural gradient was just you're going to take theta I, and you're going to say theta I plus 1 is equal to theta I plus alpha F inverse G. That's what natural gradient was. Now, this inverse was hard to compute. This alpha was hard to choose. And this whole thing was on policy, right? And the way we dealt with it was this thing's dealing with on policy. This is dealing with F inverse, and this is dealing with M. Right? And so this is just making this whole objective more practical to train with the big neural net. And the reason it's better than policy gradient is because you're still doing things that use the like natural gradient type objective, right? Which makes it more efficient, but you're doing it in a way that's practical for a big neural net. So it's better than policy gradient, but more practical than natural gradient. Does yeah, like every method, right? Like every logic. It's picture information, right? But yeah.
It is what improvement in scientific.
So I think there's an improvement in sample complexity. I don't want to cite numbers off the top of my head, but you should probably look at the paper for the exact number. It's like two orders of magnitude faster, right? Several orders of magnitude faster. But I think the more important part is that it's like able to optimize much bigger neural nets. Like it's able to optimize like things that go from vision or things that go use like a much larger function approximator than policy gradient. Like policy gradient doesn't even work in like huge parameters. And so it just like improves sample complexity, but just like enables new problems, right? Those problems weren't solved with policy gradient.
The trust region defined by essentially how many steps you take to a resample, like that's okay to kind of descend on without you.
So typically when you say trust region, you're just saying that like you want to limit the KL divergence between previous and current. And that implicitly determines how many steps that you could take, right? Because so they're like connected. But the trust region is typically just that constraint. Any more questions? Okay, good. So this is theory. We're going to skip it for now. And here are some videos. Again, we'll skip it for now because we only have like 10 minutes left. Okay, so this is TRPO. The key ideas were backtracking, line search, off policy updates, and conjugate grade. 3 key ideas. Now, what about this problem might still not be enough, right? One issue is that the advantage estimation is too high variance, right? So you're still like using the sum of rewards in the future, right? Like literally in your trajectory, and that might be too high variance. So if you remember our variance plot, we're using like a single sample estimate, but really what you want to be doing is using like something that looks like a multi-sample estimate, right? So you want to be doing things that like are lower variance than just literally taking the sum of things in your current trajectory, right? And so the problem often in policy gradient methods is that, okay, we fix all of these problems, but our objective still uses advantages, right? So our objective or Q functions, our objective, where did I write it out? Okay, I guess I didn't write it out anywhere, but our objective right here is still using advantages, right? It's still using the sum of rewards in the future. And that is like computed by just taking a batch of trajectories and doing like a sum over the future and subtracting out the average reward. The problem is that just like naively computing the sum is still high variance. And what we're going to try and do next is we're going to try and reduce the variance, right? And we're going to try and choose a better method for advantage estimation to reduce the variance. So the important thing here is that we're trying to like, basically we came up with this thing, we're trying to repair pieces of it, right? And so we repaired the covariant estimation thing, then we repaired the impracticality of policy, like natural policy gradient. Now we're saying natural policy gradient still use advantages. Can we estimate advantages better, right? Yeah.
Hessian vector product. Children just use the term Hessian to mean picture information matrix, and it's not actually Hessian.
Yes. Good question. Yeah, I think he just means matrix vector. Yeah. Okay, so how much time? 50. So I'm going to rush through this. Please look at the paper. I want to get to PPO so that you guys can get a little flavor of it. But the key idea is this idea called bootstrapping, which we like to explore a lot more when we go off policy on it. But essentially what they're saying is that an advantage, or like the thing that you weight your updates by policy gradient is essentially the sum of rewards in the future, or sum of discounted rewards in the future. So R plus gamma square, R squared, R plus gamma, R1 plus gamma R2 plus gamma squared R3, et cetera, till the end of your trajectory, minus your baseline or your value function, B plus 1, right? That is going to be the typical, like this is the thing that you have as your sum of R. This is going to be your B. And if you remember your update in policy gradient, it is grad log pi times sum of R minus B, right? That's what we did in policy gradient. We did sum of R minus B. And so that's your typical advantage estimator, and it's high variance because you still have to compute the sum over all of these time steps, and you're doing it with a single sample estimate. Now, what you can start to do is you can use the idea of bootstrapping, which is the following idea, right? So I find it kind of easiest to think about it this way, which is saying that like let's say your value function is like the expected sum of rewards, right? Your value function is your expected sum of rewards. That's the definition of the value function, right? So the value function is just like the expectation over the sum of rewards. If you remember our first lecture, a value function is the expected sum of rewards. And you can like kind of recursively decompose this by saying that this is R1 plus gamma times, you can write out the bunch of terms after the first one as, or like, let's take these ones over here. You can write out the bunch of terms after the first one as gamma times R2 plus gamma R3 plus gamma squared R4, repeat. So all we're saying is that you have R1 plus all of these terms, right? And these terms you can rewrite as, you can take a gamma out common and rewrite them as R2 plus gamma R3 plus gamma squared R4, etc., right? And so you can say that like these terms can be written like this, right? Does that make sense? So what we've done is we've said, we're just doing like recursion or dynamic programming. And we're saying that like everything after the first one, if you take a gamma out, looks like R2 plus gamma R3 plus gamma squared R4. So, and now what does that look like? Like this thing. Like, can we express this as something we know? V, right? So it's like the V at your next time step. And so you can say that your term here is basically V at S2, right? Your value function is your sum of rewards in the future, your policies. But this is just your sum of rewards starting from S2 going to the future, right? And so all you're saying is that your sum of rewards at the current time step is your instantaneous reward plus gamma times the sum of rewards in the future. Which intuitively makes sense. Your sum of reward now is like what I get now plus gamma times what I get in the future. Right? And so in the extreme case, you can say that like you can rewrite the advantage is R plus gamma V of the next time step minus V of S1, right? So essentially, this is the idea of like the Bellman update. This idea of dynamic programming is the same idea. It's just saying that like take that sum of rewards and decompose it as the first plus everything else. Take gamma out, and then everything else looks like the sum from the next step. So you can write that as R1 plus gamma V of S2 minus V of S1. V of S1 is still the baseline, right? And so let's say the baseline is the average return base. So now, you know, this only like this holds to be true only if V is perfect. If V is optimal, then this holds to be true. But if V is like some approximation, then this is going to be biased. Right? So the point here is that if basically imagine V was an approximation which is wrong, right? Then this is going to be biased because V of F2 is not actually equal to the sum of rewards. Right? So if V is an approximation, let's say, coming from a neural net or something, and if V is wrong, then this objective is going to be biased. That objective is not going to be biased because you're literally summing up things in your trajectories, but it's going to be high variance. Right? And so This is an idea called generalized advantage estimation, but it's basically saying that you can construct different estimators. On one end, you have R plus gamma B of the next time step minus V. On the other hand, you have things that sum up the whole reward and don't use this like bootstrapping update, right? And in between, you have like truncating at different horizons. And so the point here is that this is biased, but low variance, that is high variance, unbiased, right? And so you have this like trade-off between different types of estimators. And so all you're going to do is going to try and trade off bias and variance by like doing a geometric sum. So you're just going to take all of these estimators and then you're just going to like add them up with some gamma weighting or some lambda weighting, right? So you're going to say this is, this is high variance, low bias. This is high bias, low variance. Right? And the way you'd actually implement this is if you have like your baseline, right? You can get this estimator by taking your current R plus gamma times your baseline at the next step minus your baseline at the current step, right? So if this is your B, you can get the most biased estimator by taking R plus B or gamma BS2 and subtracting BS1, right? You don't have to compute the sum along the whole trajectory, just use your like baseline to give you an estimate. This is going to be biased, but low variance. This is going to be unbiased, but high variance. And you're going to like sum them up with some gamma to the J factor, right? And so the point here is that depending on your choice of, your lambda to the J factor, depending on your choice of lambda, you can like either choose this extreme or choose this extreme. So if you choose lambda equal to close to 0, you pick one extreme. You choose lambda close to 1, you choose the other extreme. And so the whole point is that it lets you like trade off bias and variance to do better here. And so here, why they have music. The interesting bit here is that this is your cost. You want to like lower is better. The things that do the best are neither things that have lambda equal to 1 or lambda equal to 0. They're things that have lambda somewhere in between. Right. And so the whole point is that you want to like your advantage estimator is still a single sample estimate. You want to do a better job there, and you want to do that by like constructing different estimators and like averaging. Yeah, I know we rushed through that, but yeah, that's the key idea. Okay, so just for the sake of time, sorry I have to rush through this, but next week we have lots of stuff to cover. So I'm gonna skip this. This is an idea called KFAC. I think it's super cool. You should read my slides. But the algorithm that we use a lot in practice is PPO, or proximal policy optimization. And the idea they kind of ask is, can we just like avoid all of this spin? Can we avoid this conjugate gradient and this inversion and like all of these like painful steps, right? And so all they're saying is like, can we just take the intuition that if we can restrict how much the policy changes in a different way, like Vishwas was asking about clipping, right? Does this like make our life easier? So essentially, TRPO says that you're going to take your objectives and put this trust region on it. It says that don't let the parameters move too much. Natural policy gain does this, TRPO does this. They're all approximations to that. And what PPO says is that you can determine how much the policy moves by just looking at this ratio, right? So it's like, if the ratio is pretty different, that means the policy likelihoods have changed a lot. The ratios are not very different. Like if the policy hasn't changed a lot, the ratios are going to be close to 1, right? And so the idea that they basically explore is that they want to do the same update, but rather than preconditioning by the Hessian and so on, all they're going to do is they're going to take this ratio and then they're just going to clip it by 1 minus epsilon, 1 plus epsilon, right? So it's saying that like the policy can change, but not more than epsilon in ratio, right? So it's the same objectives, you just split the pi theta by pi theta I. So like if pi theta by pi theta I is not more than the ratio, then it's like the normal policy gain objective. When it becomes more than the ratio, it just gets flipped off. So it doesn't let it take more steps. Right. So all that PPO is doing is it's saying, taking the same intuition and just like realizing it through clipping, which is like frustratingly easy, but like works extremely well, right? And so it's still restricting the amount the policy moves, but doing it with clipping rather than all this like second order or fish information inversion. And so the nice part about it is that because it's important sampling still, you can take multiple steps, right? And you're doing like gradient descent. No second order, no conjugate gradient, no nothing. You're just doing gradient descent on that objective. So you can take many gradient steps. You skip second order optimization, and you don't have to do any like huge inversion. You don't have to maintain any conjugate gradient procedure. You just do gradient descent on the subject. And so the key trick, the main change you need to think about from policy gradient is that we went to this important sampled objective, and then we applied clipping so that you don't change too much. And then you can combine this, like the last idea we talked about generalized advantage estimation, where you like average these estimators. You can just use that to improve your A, but the key idea here is to just like clip to prevent moving, right? And so that's kind of what tends to work the best in practice. And so people have used it for lots of different things, like the cube stuff I showed earlier, DODA, and now people use it for language models and so on, right? So same idea, realized different ways. Okay, so let's kind of consolidate really quickly, right? So we're going to talk about a paper next Tuesday. It's like PPO, the one thing we should use everywhere. And the answer is like maybe. In some domains, yes, in other domains, no. But the important points we talked about today is macro policy gradient is great, but it's impractical. So TRPO makes it more practical with 3 changes: importance sampling, conjugate gradient to avoid inversion, and backtracking line search to prevent steps. And then we said, okay, that's great, but the advantage is still a high variance, and so we do this like average of different estimators to reduce variance. And then we said, that's great, but we don't want to do any fancy stuff, so we're just going to clip, and then everything's going to be good, right? So yeah, that's kind of the structure of what we talked about. That's it for today. Real quick, we'll have discussion on Tuesday, which is an experimental format, and so we'll see how it goes. But if you are presenting, you should have got an email, and I will send you another email today just to make sure. So please come, engage in discussion, and we'll cover off policy next. Yeah. You don't have to, but it might make you able to participate in the discussion.
I didn't get anything about this. Is the big deal?
Yeah, it's on the, there's an Excel post. Let me put the names of the people presenting on there so you can also check. I'll make sure life easier. Yeah, thank you.
Still, policy, because
So it's off policy in that you can take more gradient steps.